still, at least for Thomas and module 2015, should be in at least one person.
I'm not longer than 1.5 hours.
No, I have a few slides for lunch, so.
You worked hard yesterday, yeah. I forgot to send you the...
Yeah.
Shit. The work
Oh, it's good timing, actually. I finished 5 minutes ago.
I thought that, and then because I have a visitor and so on and so forth, I couldn't stay so long.
I forgot what words was this on.
You're swap. My team.
Okay, so
That Mark was not.
Shall I get my car here?
Huh?
You want to sell my car?
so at least there is somebody from Module 15. I would say if you are ready, Amon.
As soon as I will
You still
be.
need to prepare some slides now.
We'll see.
Okay, so thanks everybody for coming to today's process of meeting without coffee, but anything, but anyhow. The reason for that is the presentation Amon is giving us on the training project he has been carrying off during how many months? 3 months? 4?
It's in the talk, but 3 months last summer and since March now.
And he has been working in collaboration with XRDtoolkit and partnered with my group. And the frame of this study is, let's say, diffraction tomography, as done by XRDtoolkit at least. And the idea is to use advanced tools for the regrouping of data, as you know. Then using the diffraction data for reconstruction, since you are rotating the sample, and we're speaking about diffraction, powder diffraction data, and visualization of these things with a framework which was proposed by us in order to visualize quickly the data in which way he will show us. And okay, Amon, I think if you want, you can start off with your presentation.
So I'll just start. So when I came here last summer, Bayo had some thing he wanted to tell me. When you're doing the X-ray experiment, it's often necessary to do a lot of data processing and data reduction on your experimental data before you can find a result that you can evaluate. And in some of the cases, the data might be bad. You have some sample that doesn't diffract well, or something like this. And if you discover this after the experiment is concluded, it's failed. So in these cases, online analysis on the beamline while you're doing the experiment can be very useful. Now, for this to be feasible, you need some software that is quick and easy to use, and it should be reasonably fast. But it doesn't have to be published grade quality of the data, just get some quick and dirty overview. In addition, it would be nice to not only give the users their data, but also some tools to process from all the way from calibrating your detector for tilts and so on, doing the azimuthal integrations, and the rest of the workflow that your particular experiment might need. So for this, he wanted me to make a software framework that could be built upon to make these tools. I started on this last summer with the detector calibration and azimuthal integrations. And this...
For those who know Israeli, it's just the same name as the library for fluorescence data, yes. But it is, has nothing to do with the thing done together with Laszlo and what you do for it. Please.
Let's probably get back to it. And now I continued as part of my master's degree to implement a particular workflow for diffraction tomography using this framework. So it's written in Python, which was chosen because it's pretty high level, so you can develop code and prototype quickly. Yet still have a very efficient code if you use the right libraries. And you don't need any license or stuff like this to use it. So for external users, it's very important that you don't have a dependency on ESRF computing infrastructure. The only thing that is required are some Python libraries that are readily available.
You have stick there.
This is not that readily available, but it's a branch of SciPy, so it's going to be adopted and okay. It's used mostly for tomographic reconstruction. Installation should, in principle, be pretty simple. If you have access to a machine, you can do a site-wide installation, just like this. And it should get all the dependencies for you. And for a developed version, you can work on your code, just import the library, and it will update as you change code. It's very easy to work with. Why would you want to use this thing? Well, so far it doesn't have too much. It has some old code that was rewritten from Vaio's MATLAB script for doing cross-section calculations, form factors, simulation examples, and so on. And I've done a lot of file input-output, reading and writing to HDF5 files, which is a hierarchy. It's like a container, you can put lots of data sets in it and then group them and so on. So it's quite flexible and optimized for large arrays. So I have some utilities for reading this. You can specify a whole list of files that you will read, even multi-frame EDF files. So this X-ray lib that I've written so far, it's only good for doing some crude processing. Claudio already mentioned Dawn, which is software developed in collaboration with Diamond. It's very nice for data exploration. If you have your data, you can slice it along the different dimensions and do peak fitting and simple stuff like this. It's very nice for this, but it also has started some workflow integrated that also uses Python. So it would be possible to try to integrate these two, but it's still in high development and not too much documentation, so I didn't spend too much time to try this integration. So for what I've done, I've just used this for visualization. Some structure. It's pretty nice to try to keep things modular and not redo things. So we have these external libraries at the bottom that provide quick integration, file access, image manipulations, and so on. And on top of this, I made some utility functions. The X-Ray lib, which is a Python module that you can import, and you try to put all the functionality there, which you then use in the different scripts. That's just an interface. I've gone for just a command line. You go to the command line and you have these X-ray lib dash, calibrate, integrate, sample, and so on. We just use this module. So an alternative way could be to make some DOM workflows, which also is Python based, but this is on the to-do future. Finally, just for convenience, there are some example shell scripts for if you want to do a whole lot of integrations Depends on the file structure and so on, and each being line, so that could be provided. So current applications, we have some simple workflows. Last summer I did some azimuthal integration for data that had some parameters like temperature or angle or something like this. We'll do the integration and then assemble a nice volume. This script, X-Ray calibrate, just takes in the dark current and the reference sample, and then it tries to. Then it assumes that the rings from the reference sample are perfectly circular. So it divides into sectors and integrates, and when the image is properly calibrated, it should be equal intensity. So there's some least square regression on this. First in the origin of the beam and then the tilts. I found it might get stuck in some local minimum if you try to do both simultaneously for the start. And the tilts are very small, so you can do this afterwards. So this is how you would invoke it from the command line as it is. So there are quite a few options, and you don't really need all of them. Strictly speaking, you only need the detector name and the calibration image. And we'll try to find everything and write the resulting geometry to file that pyFAI can read and use for the integration. So here you have the integration. You have a stack of integration images that you pass to the X-Ray integrate script, which also takes the geometry file that you got from the calibration stage. Then it will parse the file names delimited by underscore to see if there are several parameters which are varying. Here you have a 3 by 2. So you have some parameter here, temperature for instance, and angle here. And we will try to put it into this for you. In the interface. So already this can be useful, because you will see if you have some diffraction and so on. For diffraction tomma, you want to look at some particular phase. In diffraction tomography, you do a scan along the sample for different orientations, and you get a cavity profile for each of these data points. What you do is you can select one phase for a 2 theta value. That I've done in DAW by loading up the diffraction, the diffractogram, and then do some peak fitting to get the position and the width of the peak, which we then pass to X-Ray assembly script. So a advantage of doing this peak fitting is it's pretty robust. You don't have to do a lot of corrections on the data itself, like air scattering, or since you fit it to a linear background, and you only use, for instance, the area of the Gaussian peak. And since it's really nice, you will output the fitted peaks and the data it used, so you can inspect and see that it's doing a good job. Again, it should be quite simple to use this. You can specify one peak on the command line with a position and shape and width, or you can specify a file with peaks exported from DAW. So then you should have some hopefully nice sinograms. You can still do some corrections on them, which you have another script to do. And finally do the reconstruction. And all this is stored in the same file. grouped into groups, so it's easy to navigate. So for the corrections, it might be necessary. When you're doing the scans, you often want to scan on the way to the left and the right as you go over the sample to save time. And then what you might have is every odd row in the cyanogram will be shifted respective to the even ones. So you get this zigzag pattern. So what this script will do for you, it will split the two images and then correlate them and figure out how much you need to shift to make it overlap better. And the same for the center of the sample, it can be refined as well and shifted, which gives less artifact in the final image. So just 2 weeks ago, I had some beam time and I took some data. I prepared a small piece of glass spheres and some wax and made it stick to a tip of needle to test my tools. This is what it looks like. I think my scan, it should be in this area, and I just have one slice, unfortunately. So we will see some of the cyanograms and the automatically corrected ones and their reconstructions. Using just filtered back projection because the SART was not available on my laptop.
Could you see which code you used or you programmed for filter back projection algorithm?
Yeah, so that's the scikit image library, which has these methods. I looked into pyHST, which is really it has a lot of features, so I tried most of my time to turn them off because I just need some simple, really simple inverse rate and transform. And it's less dependencies if you want to have it self-contained. Here's the cyanogram of the VAX phase. The reconstruction of the VAX phase. You can see there are some voids where you have the glass spheres. This is the cyanogram that it was reconstructed from, without the corrections. So I don't know if you can see kind of jagged lines, which in the correct version is a bit better.
What did you use to visualize this?
This is screenshots from Dom.
From Dom.
From Dom. And they're reconstructed from the correct cyanogram. It's not much difference for this phase, but here you can see for glass spheres you have lots of artifacts. You have some nice streaks originating from this position. It's not very clear. If you see the cyanogram, you understand why you have these big spots here. So if you look really carefully, they kind of follow the sinusoid, so it implies they're from the same place in the sample when it's rotated. So most likely this is some crystallized, some diffracting thing, which for some angles, some projections, are highly diffracting and disturbs the cyanogram. So what they've done is some simple outline rejection to use medium filtering at just these spots to remove them.
So it means if you have a grainy sample, it doesn't work well.
If you have a grainy sample or some sample with a preferred orientation, it's not going to be that good because you're assuming that for every projection has kind of the same scattering power throughout the sample. So in my sample, I think it might be the wax or some piece of aluminum foil which I used in preparation that's stuck in there somewhere. But anyway, after removing these biggest spots, it's much better for the reconstruction. Now I think for this one, it's been filtered a bit too much. So I should put in some restriction that if more than 10 or 15% of the image is registered as outliers, you should just reject and do nothing. So I thought this was promising for something automated and quick and dirty. So get some reconstructions, small fractions. So issues with this, not everyone is comfortable working from the command lines. So it would be nice to have some graphical interface to X-Ray Lib and functionality. Just quickly to turn it on. I'm pretty sure that I didn't have enough time to look more into it. And Vimlans could provide some presets if they just use one detector or two detectors. They could have some pre-made scripts for just doing the calibration. Yes. So as much as finished solution as the framework to build upon. So for the work, there are some. I started with some unit testing of just the sample calculations, the form factors, attenuation coefficients, and so on. But it should be extended. Testing is very nice when you have some library and thing breaks will change, but there's never time. So the biggest problem. Do you have any suggestions for what we could call this?
X-Ray Diffraction.
X-Ray. Yet not the X-ray yet.
Why don't you integrate it in pyMCA, for example?
Integrate.
It's not forbidden. From pyMCA import X-Ray.
It is an option. It is he knows about that. Yes.
To integrate the
it could become a part of pyMCA.
No, it is absolutely an option. Only cannot do it because he's leaving tomorrow. But
Why do you need a name? There are already so many names.
Yes, no name.
well, it could be the name of a button in pyMCA. Yes.
Yeah.
Okay, good. So now will you give the demonstrations now?
Yeah, I'll see if it works on the Wi-Fi. It's
Just one question again for this diffraction promo. You said
Yes.
if it's grainy or textured, it doesn't work well. But you work on the radial integrated.
Yeah, you
At
use
the
the-
end, if you get a radial integration out,
Azimuthal.
I've been told if it's too textured, it's not good. But
well, I say it's
myself, I don't know.
It depends on the direction, right?
no, but you can select after if you do the radial integration, you
Yeah.
lose this 2D info, but you just have one pattern.
Yeah,
Yes,
but
but
then
still-
you have
then you
not
take
a
the
rotation.
But the same volume.
Okay,
It's
so,
not giving you the same pattern.
you lose the peak while you're rotating.
Yeah.
This is a subject of research, right? To reconstruct the texture and